So today we'll be talking about assignment 4, which is a genetic algorithm. And that genetic algorithm is going to solve a bunch of different things. That's the great thing about a genetic algorithm. You write one algorithm, and it can solve whatever fitness function you give to it. But kind of the domain that we'll be working in is in the Sudoku. So who has played Sudoku before? Anyone? So most people know what Sudoku is. But just in case there's someone in the class who doesn't know what Sudoku is, explaining the rules is very easy. So over here we have, this is just sudoku.com to show you the rules over here. So we have a board, and that board, the standard Sudoku board, is a 9x9 grid. And the object of Sudoku is you are given some partially filled out grid, and then what you have to do is fill in the numbers that meet 3 conditions. So one condition is that all the numbers 1 through 9 appear horizontally in each row without being repeated. And then that condition is also true of vertically in each column and also in each of these squares, right? So for example, in this top left square up here, we do not have a 1, we do not have a 2, we do not have a 7. So I would have to put in 1, 2, 7, and 5. So I have to put the numbers 1, 2, 7, and 5 in here so that they don't collide with any of those conditions that we set. And that's it. You go through filling out one by one. You, for example, look, okay, I know I have to put a 1 somewhere, but there's a 1 in this row, there's a 1 in this row, and there's a 1 in this column. So I know through the power of deduction that there must be a 1 there. And then you iterate that 80 times until you've filled up the whole grid. Now, we're not going to be solving a Sudoku board in this way, in the assignment where I give you some things that are already filled out. But what we're going to be doing is using a genetic algorithm to just come up with a Sudoku board that is solved. Okay, so we're just going to generate numbers. And if I gave you this to do as a human, you'd just write 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 2, 3, 4, 5, 6, 7. It's trivial to generate one on your own. But what we're going to do is we're going to start with random numbers, and we're going to use a GA to perturb those numbers and use the evolve function that we saw in the last lecture to turn that randomized board into a solved board. Okay? And we'll also see some other things that we're going to solve. And of course, we always give you, or not we, I always give you a user interface, and then you have to write the back end. Now this looks a little bit complicated, but trust me, it's probably, I would say this is the easiest assignment of all the assignments. I saw a few smiles there. I know that the last couple of assignments have been a bit of work, but the assignment 4 and 5 are probably the easiest 2 assignments. So in this one, over here on the left, you have the visualization of a Sudoku board, and over on the right, you have a graph. I'll get back to the graph in a second. But over here, you see, so this is running a genetic algorithm. As part of a genetic algorithm, you have a population, and so there's so many individuals in that population. And what's being displayed over here is the fittest individual of the current population. So you've been running this genetic algorithm for a while, and whatever the top fitness one is, I find that in your population, and I draw it on the board, on the screen right there. And what the colors mean is the colors are some sort of visualization toward the solvedness of a Sudoku board, right? So the colors here, if they go white, light red, medium red, and dark red. And so the darker the red, the more conflicts there are with that particular square. So up here, for example, the darkest piece I see here is this 4 because there's a 4 here, so that's one conflict, and then there's a 4 down here, so that's another conflict. If there was another 4 in here, it would be the darkest shade of red. So if I hit refresh, you'll see a bunch of these super dark shades of red, and then the board gets lighter and lighter and lighter as it gets solved. Okay, so if there are no conflicts, so for example, this 1 is the only one in the row, it's the only one in the column, and it's the only one in the square, therefore it has no conflicts. So what this does is it just gives us some sort of notion of how solved the board is. But of course, as a Sudoku player, as most of you are, you will know that it doesn't really count to be an almost solved Sudoku board. You could have like 80 of the 81 numbers in there, and fitting that last number, you might have to take half the numbers off the board just to put this one in. And so this is sort of intentional by me to show you what I've done here is I've included a few convex problems, and Sudoku is one of the least convex problems that I've ever seen. So what do I mean by a convex problem? We showed in the last lecture that some problems are convex and some problems are not. And so non-convex problems are going to have a bunch of local minima that we can get stuck in, like Sudoku, right? We can get closer and closer and closer to a solved board, but at some point we can't get any more solved without unsolving a bunch of the rest of it. So Sudoku is a particularly punishing problem, and that's by design in this assignment. If a problem is convex, meaning that we can always take any current solution, and without going backwards, we can get toward a solution, then genetic algorithms solve that really easily. So down here, I've included a bunch of convex problems as well. So for example, here is the sum values fitness. So so I guess let's explain the user interface. We have our options down in the bottom left, and I realize that they are probably too small for you to read here, but I can't make it any bigger without this going off the screen. So the first option down here is to change the fitness function. So if I change it from Sudoku to sum values, then my fitness function changes to just be the sum of all the values, right? And if you think of this function, it's pretty easy to be able to take a current board and make it better, right? I don't need to unset some numbers to set some other numbers as higher. So this is a convex problem. And so genetic algorithms can solve this very, very easily, right? And so you see that we've already reached the maximum fitness. All the things over here are 9s. So now I guess it's a good time to explain what this graph is. So this graph shows over time. So just like previous assignments, this assignment, the visualization kind of runs on a timer. And so it's 60 frames per second. And so once every frame, it will generate a new generation. So if your algorithm is running fast enough, you'll be doing 60 generations per second. And whenever there's so many generations done, it will plot this on the graph. And so the x-axis is the generation number. You can see we're already up to like 3,000 here. And the y value is the fitness value on the y value. So here we have 3 different lines. One is the max, one is the average, and one is the minimum. So as you can probably imagine, the max represents the fitness of the maxed fitness individual in the current population. The average is the average of all the fitnesses in the population, and the minimum is the minimum of all the fitnesses in the population. And let's continue to go down here. Let me make this just a, no, I'm gonna leave it that size, or can I make it bigger? Okay, let's full screen it, make it a little bit bigger. Okay, that's as big as I can get it. So down here, there are some more options. The first one is population size. So if you slide this, it actually edits the running genetic algorithm in real time. So it changes the options that you are using for that. So now, instead of there being 100 individuals per population, there are 500. So if I come here and I go back down to some values and I switch it up to 500, ideally, now you will be solving the problem in fewer generations. Because if there's more individuals in the population, your gene pool is healthier, so you can solve the problem a bit faster. But because a genetic algorithm is sort of a linear running time, because you have to do the same operations to everything in the population, then it will take longer per population. So that's the trade-off whenever you do a genetic algorithm, is you have to say, okay, what is the trade-off between the increase in per generation performance of having a higher population versus how much longer will that actually take me to run? So genetic algorithms are all about turning a bunch of knobs until you get the right solution, and that's one of the knobs that you can turn. Down here, we have the number of individuals that get mutated. So after we generate a child, we pass it into this mutation function, and I'll go over the code of all that later. And this currently says that mutate 20% of the individuals. And by default, for our assignment, a mutation just means taking one of the numbers and randomly changing it to a 1 to a 9. Okay, so if it was a 7, now you just choose a random number and it becomes a 1 or a 9. Next is the amount of random genes that get inserted. So for example, let me refresh here. So if I start with a population size of 100 and I have a percentage random genes inserted as 5, then 5% of 100 is just 5. And so every generation I put 5 completely random genes into the next population before I do my child generation. So if I bump this up, then I'll have more randomness in the gene pool. And look what happened. what did you see happen on the graph there when I did that? Okay. So over on the graph, if you didn't notice, the average went way down. Why is that? Well, this is going to take the fitness of all the things in the population, and if I'm inserting a bunch more random things typically have a very low fitness, right? And so if I put in a bunch more things that have low fitness, then the average fitness is going to go down, right? Makes intuitive sense. Now, you can see here, well, why didn't the minimum go down, right? The minimum didn't go down in this case because even though we put in more random things, there were random things before, and a random Sudoku board isn't going to vary dramatically in its fitness function, right? It's going to be pretty much around the same fitness. But if you have a particular environment in which more random things, it could be very low, then maybe you will see your minimum line go drastically down. You can see sort of, if you had maybe a linear regression here, it would go down a little bit, but it didn't go down a lot. Similarly, if I set random genes to 0, what's going to happen down here? Well, if I have no random genes, then the minimum goes way up, right? Because there's no minimums there's no terrible fitnesses going in there anymore. Now, this is another trade-off in genetic algorithms. If I don't have any randomness in there, then my minimum is going to go way up, but maybe now my gene pool is stagnating, right? Because the only variation I have in my gene pool now is the mutations. If I have nothing random that I could randomly select to breed with at some point, then my gene pool is not very, is not getting great. And you can see here that I'm kind of stuck in this local maxima here. I can't, it hasn't been solving this any further since for the last minute or so. Down on the bottom is the percentage elite gene survival. And if you remember what elite gene survival is, it literally just says, take this percentage of the top genes from the previous population and ensure that they survive to the next population. So this will say I have 10% elite gene survival, I have a population size of 100, so the very first thing I do when I go to form a new population is I take the top 10 fitness genes from the previous population and put them into the next population. Now, what does that ensure on the graph? Well, an elite gene survival ensures that my maximum fitness can never go down. If I have at least one elite gene survival, it means I'm at least taking the best thing from the last generation, carrying it over to the next generation. And so my top can never go down. So that's a good thing. We're always making some sort of progress. But down here, if I then go and turn my elite survival all the way down, so if I put it all the way down to 2, okay, you can see the average fitness and the min fitness going down, because if I'm not taking as many fit things over, then that's going over. But if I drop it down to 0, well, look, now my max is going way down. Why is it going way down? Well, because I have no guarantee that the best thing that I had from the last iteration is actually going to be surviving, right? So you can see immediately how much of a difference that makes. And so elite gene survival is pretty nice to guarantee that at least something. And so now, okay, it's re-evolving back and back from where it was. So if we ever do get stuck in a local minima for a GA, what we can do is just throw a whole bunch of randomness in there, throw away the current best, and then maybe start learning again. There's all sorts of things that little tricks that we can do to, say, stir up the gene pool. Or for example, one little trick that they do in the literature is say, okay, the percentage of individuals that get mutated or the random number of genes that get inserted, this is actually a dynamic value. So I'm keeping track of how much I'm evolving. And if I've sort of stagnated, then maybe bump up those values temporarily. And then if I start learning again, put those back down, right? So there's all sorts of little tricks that we can do, and you get to see in real time. And I think it's a nice visualization of what's going on. So let's have another look. Let's refresh this to the default values. And then we'll look at the other fitness functions that I have. So this one says match row. And so what this does is it just says, give it 1 fitness if the number in the cell matches the row number. So it should be all the things in the first row are 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that solved that pretty easily. Because again, this is a convex function. Match column, opposite thing. right, where we'll have the gradient going from left to right. And in this visualization, I've essentially just colored the numbers scaling from 1 to 9, white to red. And if I go down here to a checkerboard pattern, it's a 1 or a 9 forming a checkerboard or a chessboard pattern, right? So the cool thing is my algorithm literally has not changed to solve all of these different problems. That's a really cool thing about a genetic algorithm, is all you have to do is tell it the thing that you want to see, and it will get that thing for you. Now, that being said, if you really want performance in a particular domain, for Sudoku, for example, you might have a bunch of Sudoku-specific things, right? So for example, if you were trying to solve Sudoku at a really high level, then maybe how you take the how you do the crossover might be interesting. So for example, in this assignment, all I'm saying is take the gene, split it down the middle, take the first half of one and the second half of the other, and that's your child. But does it really make sense to split a Sudoku at the middle piece? Right? Maybe you want to combine them by rows or by columns or by squares or something like that that's a little bit more domain specific. So the cool thing about GAs is that yes, one algorithm can just solve any problem, but, well, I'm saying solve. It can work toward the solution of any problem. But if you do want to include some domain specific things that may help you, so for example, another thing in Sudoku is, well, if you think about it, any solved Sudoku board is going to have 9 1s, 9 2s, 9 3s, 9 4s, etc., right? So maybe instead of changing something to a random value, because now you might have 11 1s on the board, maybe instead your mutation is, I'm going to swap the location of two things, right? If I start off with exactly the right number of pieces, then maybe swapping is better than randomly setting. I don't know, but we're just going with the default sort of swapping, and I'll get all into that. But it's really cool how GAs work and how you can visualize this in the assignment. Next, I want to explain how the phenotype versus genotype works in this particular assignment. So as you remember from the last lecture, the phenotype is the actual real-world representation of something. So the phenotype would be like the muscles, and the genotype would be the DNA strand or something like that represent how the muscles get formed. So it's not quite that dramatic of a difference here, but for our Sudoku problem, the phenotype is the Sudoku board that has those rules applied to it, like it's a 2D grid, and the genotype is just a 1D array. So the genotype is going to be 879254653652813. So I just take it and unroll it into one array, and then basically all I do is draw it as a 2D array, right? So there's the genotype that we actually work with for mutation and recombination is a 1D array. That's the gene, that's the DNA of the Sudoku board. And this is just a simple example where you just take that and turn it into a 2D to get the phenotype. But you could think of, an arbitrary video game, maybe a Mario level or something like that, where you have a 1D genetic algorithm integer representation, and then how do I turn that into a level? Well, it might be a much more complex function than just turning it into a 2D structure. Okay, so also I can change the size of the board here, so I can solve this. There we go. I've solved a 2x2 Sudoku. It is actually remarkably hard to solve the 3x3 Sudoku. A couple of people have done it when they left it running overnight, or they made very specific modifications to the fitness function and stuff to make it work specifically for Sudoku. But my naive solution here has never even come close to actually solving the 3x3. So let's look at the code of the assignment. So over here we can see all the different files that you get with the assignment, and of course it's the standard thing that we've done already, where you have a few things that are related to the UI, and then there's some sort of environment representation. So the environment representation is this Sudoku class that I have here, and so the Sudoku the Sudoku class, it has a constructor and it takes in a size. So for example, for this to be the default Sudoku, this would be excuse me, I would pass in 9 to the constructor. Okay, so a 9x9 Sudoku board. So this.size equals size. These are the class variables of the Sudoku board. The square size, that is just so when I go to iterate to check the squares for the fitness, that's going to be 3, so it's just the square root of the input number. Then I have a board that I'm going to be storing here, and I say, okay, the board is a 1D representation of the Sudoku board, and when I construct a new Sudoku board, I just give it a value of all zeros. Okay, so that's the constructor for the Sudoku board. Now, because this is a 1D storage of a Sudoku board, we're going to need to somehow translate the 1D index into the row column, and vice versa, where we want to say, get me row 3, column 4, and turn that into the 1D. So that's really easy. I'm sure you can all do that by now. It's just the size times row. So size is the number of rows and the number of columns plus column. So we go down a number of rows and then over based on the row or column that you get. Really simple calculation. This function here, if you need this for whatever reason, this just creates a randomized Sudoku board. So it takes the current board and just completely randomizes it. This is mostly in there so that you can steal it for your own purposes if you need to generate a random number. So just math.random, that'll generate a random number between 0 and 1. Then I multiply that by the size to get a number between 0 and 9. But that's still a floating point number, so then I floor that number, and then I add 1 to it. Okay? And the reason I don't just seal the number is because there's a small possibility that that doesn't work. There's like an edge case, so I think sealing doesn't work. Yes, because if you seal it, you'll never get a 0, right? Or you'll, no. Yeah, anyway, I think you might be able to seal it. But anyway, I've done it this way. Whatever. This way worked for me, so I floored it and added 1. I think there might be some weird edge case, but either way, that doesn't matter. There's a set function, which will set a given row column to a specific value. There's a get function. This is probably the one that you'll be using most to be able to look at the board and see what's at a particular row value. And then I've written a little function here, which is num conflicts with a row and column. So this gets the row conflicts, it gets the column conflicts, and then it gets the square conflicts, and then it returns that sum. Okay, so that's what I use for the fitness value. It's just the no, sorry, that's not what I use for the fitness value. The actual fitness value, which I haven't talked about yet, you're like, oh, what is this fitness value? So if I look at a particular cell, I'm going to say, okay, is this unique in rows? Yes, that's a +1. Is it unique in columns? Yes, that's a +1. Is it unique in the square? Yes, that's another +1. And so I sum that value. So each cell has a value between 0 and 3. 3 is good. I want it to be unique in rows, columns, and squares. And then I just sum that value over here. So whatever 81 times 3 is, that would be the maximum fitness function for any solved Sudoku board. So that was just my attempt to take a Sudoku board and apply a fitness function to it. However, part of this assignment is going to be you writing a better fitness function. Why? Well, if we think about the roulette wheel selection algorithm that we talked about last time, that's what you're going to be implementing for this assignment, is the roulette wheel selection. Well, my fitnesses for this board vary between 0. If like everything on the board was a 9, right, it would be a 0 because it would have no uniqueness anywhere. If I had a completely solved board, that would be, what's 81 times 3? 270, 243. 243, okay. So what do I have here? Yeah, so 243. That's way easier than I thought it was. I don't know why I said 270. So it goes from 0 to 243. But look at this. The minimum fitness that I have is like 150. In any given population, even if I generate a random one, it's 150. So just think to yourself, roulette wheel selection. The worst possible thing that you can generate, almost, is random. Do you really want a random individual having a fitness of 156 and the best possible thing you could get having 240? That means that the worst thing that you're generating has more than a half chance of being selected against the best thing. Typically, you'd want the best thing to have like 1,000 times chance of the worst thing of being selected, right? So you're going to have to sit on that for a little while and think about, how could I take this value and make the really good things a lot better than the really bad things. So some trivial examples of how you would do that: take the number and square it, for example. If you take a number and you square it, then the bigger numbers grow faster than the smaller numbers, and so maybe you would have that. But if you square these numbers, still, you're only getting, a slightly better chance of picking the top things. You say, well, I'll just take it to the 10th power or something like that. No, I want you to actually come up with maybe a better Sudoku fitness function than that. So that's part of the assignment. So I forgot to say all of that when I was initially going over that. But yes, you do have to come up with a better fitness function for Sudoku. And that's the reason. And it's because all of these fitness functions, like even if something is super close to being solved, right? Like it has everything but 2. That would be 241, which is only like a 1% difference from being solved. But it's a lot better to be completely solved than to be almost solved, right? So you're going to have to come up with something to spread those values out, or having a better than linear chance. That's what I'll say, right? And what do I mean by linear here? I'm saying that just assigning a linear value to the number of conflicts, or the inverse of the number of conflicts, is probably not a good fitness function, and that's probably why I'm not solving it here. Okay, so let's go back. So that's just one example of how you might calculate some values like that. So you're free to use this code if you want to as sample code. And then this set array, what this does is, for the user interface, I take the maximum valued, I'm drawing a particular board that's stored in the UI, and then I take your maximum valued gene and I use the set array function so that it becomes the maximum valued one. So that's sort of a helper function for me more than anything else. So that's the Sudoku class. It does basic Sudoku things and is just there for your convenience. The next one is the GA settings class. So if first we go back over here and we look at all the different settings that we have. So we're going to have right here a fitness function, right? That's a fitness function. We have the size of the board that I can change. I have the population size. I have the number of individuals that we mutate, the number of random genes that I insert, and the number of elite genes that survive. So my big tip for anyone doing any sort of AI programming where there's configs involved, and we've been doing this the whole year, is form a nice little class that stores all the settings or all the parameters or all the config, and that's what I've done right here. So I have a GA settings class, and the constructor to that class is just the size of the Sudoku. And so the fitness function, one of the cool things about JavaScript, and this is true of most programming languages these days, is that I can store a function as a variable, right? So when I go through the UI and I check a different thing, I just set the function to something else, and then if you want to call the fitness function, you just say settings.fitnessFunction. And then in the parameters of that, you pass in your gene, and it will calculate the fitness for you. So whatever I have set the fitness to over here, whether, whatever one this is, whenever you call that in your GA, it will be calling the correct fitness function. So the fitness function gets set here. The individual size, that is the number of integers in the GA gene representation. So if the Sudoku size is 9, then this will be 81. So that's what I've set up here. The population size initially is the values of what I have in the UI, but as you change those elements in the UI, it dynamically updates this, right? So you never have to worry about that. Every single iteration, the user interface is going to pass in the new settings object to your evolve function. This is the elitism ratio. So this is expressed as a ratio, so 10% means 0.1. And what this means is that you will take 10% of the 100 top fitness individuals and carry them forward to the next generation. The mutation rate is 0.2, so that's 20%. You're going to mutate 20% of the things. And that doesn't mean that every single time in every population you mutate exactly 20%. What I do in the solution is in my mutate function, I generate a random number between 0 and 1, and if that's less than 0.2, I do the mutation. So if I get really unlucky, maybe I only mutate 10 things, one generation. Maybe if I get, if it gets really lucky, I'm not saying, lucky. I'm saying less than or higher than. If the randomness is off, I could mutate everything because it's a random chance, right? But that's fine. I don't want you to like ensure that, okay, I'm going to generate an array and put exactly 20 ones in it and then check against it. It's fine. I'll get into that when I look at the pseudocode. Similarly, this is the random ratio, so how many, what percentage, this is 5% of population size that we would generate as random. And this down here, says for I equals 1 less than or equals Sudoku size, this dot individual values dot push I. So what this means is that, how do I explain this? So for every possible space in the board, there is a bunch of random legal values that I could possibly have there. For Sudoku, it just happens to be 1 to the Sudoku size, right? So here, this stores for each of the possible locations all of the different things that it could be. So it loops from 1 to Sudoku size, so from 1 to 9, and adds that to the array, right? So whenever I want to, for example, generate a random gene value, I want it to be one of these legal individual values. So I actually have a function down here which does this, so get random gene value. So when you go to mutate something in your Sudoku board, instead of you having to say, get me a random number between 1 and 9, it will actually, this does it for you. So if you say settings.getRandomGeneValue, it looks up the individual values, generates a random number between 1 and its length, and then floors it. And then that's what it does. So it's an array with 1 to 9 in it, generates a random index, and then returns that value for you. So if you want to get a random gene value, you can just use this function. You don't have to generate that yourself. Here in the settings, I have all the different fitness functions that I wrote. So this is the sum fitness. This gets passed in an array, and that is the genotype representation of that Sudoku board, right? So this is an array of length 81 if the size is 9, and I just have a sum, and I add everything to the sum and then return that. So the higher the sum, the better. Checker fitness, this just goes through and says, okay, is the sum of the row and column an odd number or an even number? That's an easy way to generate a checkerboard. And then it returns that. Match row fitness, it just says, is the number the same as the row? And match column fitness says, is the number the same as the column? So you can see here that the Sudoku fitness is missing, and that's on purpose, because you're only submitting one file for your assignment, and that file is, over here, GA student. And GA student, at the very bottom, contains Sudoku fitness. So whatever you put in here will be the Sudoku fitness that's used for the assignment, and this is where you put your Sudoku fitness. So this is the first thing that I'll describe in GA student, which is the file that you are going to be doing all your clever. I just read the word clever and said it out loud. Well, you'd be doing all your coding, hopefully clever coding. So this says, rewrite this function to be more clever. See if you can modify this function so that the GA gets closer to solving the Sudoku than the version listed here. Due to the way roulette wheel selection works, this function must return a higher fitness for a better solution. You cannot return negative fitnesses. Okay? So don't put any negative numbers here because it just breaks roulette wheel selection. Because roulette wheel selection relies on the sum of everything, if you can recall from the previous lecture, and negative values will, like, if you have the sum be 0, then it'll just like mess up all the chances. So make sure all of your fitnesses are between 0 and whatever. And so this goes through, adds the unique values in each row, adds the unique value in each column, adds unique values in each square, and then returns that. So you'll take that as your inspiration code, and you will make this a little bit more intelligent. How much more intelligent? I always get that question. How much more intelligent do we have to be? Sir, is this good enough? Sir, is this good enough? As long as it's doing something non-trivial. Okay? Now, I don't want you to just go Google Sudoku GA fitness function and copy and paste it. Normally, I do let you go do that thing, but I really want you to work on that yourself. And also, as a requirement, tell me what the hell is going on. I just want to see in English, like, your explanation of what your fitness function is doing. And I do not I am not going to allow you to just take this function and return fitness times fitness times fitness times fitness to, like, you know, take it to the power of 4 to do that little trick that I mentioned before. Okay? Do something a little bit clever that actually modifies the way that you're calculating Sudoku fitness. Okay, now let's quickly look at the PowerPoint slides from last time. So here we have, this is the evolutionary algorithm framework, right? This is the big framework. So this is initialize the population with random individuals and then repeat until there's some termination condition. So the initialization of random individuals, that is done by the UI. You do not have to do that part. The repeat until while loop, that is done by the UI. And then it is going to call your evolve function, and the evolve function does steps 3 through 7. So the GA evolve function, which I have here, is the thing inside this while loop that does these 5 steps. So you're going to evaluate the population, select the parents, combine the parents, mutate the offspring, and then form the next population. Okay? So let's have a look at that. The first thing I have to do is quickly talk about, I've described this in theory already, that the phenotype is the 2D Sudoku board. The genotype is the one-dimensional representation of that. And so you may think that a population then is simply an array of 81 length arrays, which in theory it is, but in practice, to make your lives a little bit easier, instead of just having an array of arrays, I have an array of JavaScript objects. Because associated with a particular gene is its fitness. And if you don't store the gene with the fitness in the same object, then you're going to have one big array of fitnesses and one big array of genes, and it's a nightmare to work with, because one of the things we're going to be doing is sorting the population based on fitness. If you have the fitnesses over here and the genes over here, yes, it can be done, but you don't, trust me, you don't want to do that. So here, an individual in a population is a JavaScript object with one variable called gene and one variable called fitness. The gene is the 1D array representation of the individual, and the fitness is the fitness of the individual, and we calculate this when we construct the individual. Okay? So then a population is going to be simply a JavaScript array of these objects. Okay? So you'll take array population I.gene, that is the ith individual's gene, and population I.fitness, that is the fitness of the individual. So what I've done is I've very nicely put in a bunch of comments in that evolve function, which tell you what you have to do in what order, right? Rather than just leave it blank. So the first thing that we're going to do, also this takes in the settings. So settings, if you forget what's in settings, you can just go over to the GA settings object, and that's what this is. It's a GA settings object. So the first thing that you do is you set up a new array, which will hold the next population. You do not have to change that line of code, just a normal JavaScript array. And if you somehow think, I'm going to use a more clever data structure than this, you will absolutely break the UI. So please don't do that. Sorry, you can't be more clever, but it's fine just having a JavaScript array. The next thing you're going to do is, okay, I've been passed in a population. I'm going to sort that population descending based on fitness. I'm not going to give you the code for that because you've got to do something, for this assignment. So each of those JavaScript objects is going to be sorted based on the fitness value of that object, and that's literally a one line of code. I think it's array.sort and whatever. So and the reason we want to sort things is because next we want to take the top n things from this array and put it into the next population. And so that's much easier to do if it's sorted. So add the top n elite, top fitness individuals to the next population. The percentage of elite genes to carry over is given in settings.elitism ratio. Sorting the population array by fitness is an easy way to do this. So literally all you have to do here is take, now, how many do you carry over? There's two values here indicating the size of the population. One is population.length. The other is settings. Where's GA settings? Population size. So for this case, please use settings.population size. The reason is, if you don't take the population size from the settings, you will never incorporate any changes if you change the setting size in your slider. If all you ever do is take population.length, then you'll take the initial population's length over and over and over, and it will never change. So grab the length from settings. So all you have to do here, super easy, settings.elitism ratio times settings.population size. That is the number of the top things from the previous one to carry over to the next one. Super simple. So now you've got a new population with possibly some things in it already. So for example, if the population size was 100 and then elitism ratio was 10, you've already got 10 things in this new population. So what do you have to do? The next thing, add some random individuals. Okay? So add the required number of random individuals to the next population. The percentage of random genes to carry over is given in settings.elitism ratio, or random ratio. So again, settings.random ratio times settings.population size. That's the number of random genes that I want to create and then add into this next population. So if that was 5, by the end of this one, add it to the 10. Now my next population has 15 things in it already before I've done any crossover, any actual breeding of the objects. You can get a random gene value by calling settings.randomGeneValue. Make sure to add the following object to the array whenever adding an individual. Remember, individuals are objects, and you go next population.push, here's the gene variable. So you're going to create a new 1D array of whatever the correct length is, that's in the settings. For each of those, you're going to give it a random gene value, which you get by settings.randomGeneValue, and then you call settings.fitnessFunction gene variable, and that's it. You can actually just uncomment this line, and if you create gene variable, it's done for you. Okay, so that line is actually valid JavaScript. It just creates it in place like this. And so if you uncomment out that line and create gene variable correctly, that's done for you. Okay, now we've got 15 things in the next population. So what do we have to do? Well, the remaining step is to say, well, I've got a particular population target size. I have a particular number I've created already. So while I am not full, create more children. Okay? So we keep adding children until we fill the next population. But first, if I'm going to be doing roulette wheel selection, part of roulette wheel selection, if I go here, part of roulette wheel selection, which is what we're going to be doing, is calculating the sum of the population fitness. Right? So since I'm going to be doing roulette wheel selection a number of times, yes, I could calculate the sum of the population each time, but that's a bit of a waste. So what I'm going to do is I'm going to, like in this function here where I do roulette wheel selection, I get passed in a population, I calculate the sum, but just to make it a bit faster in our assignment, I'm going to make the roulette wheel selection take in another value, which is a pre-calculated sum, so we don't have to do that over and over and over again. So let fitness sum equal. Here you will just calculate the sum of all the things in the population, and then you will have the sum. So we're going to pass that in. And if we go up here, oh, actually let me do this first. So this says, while population is smaller than settings.population size. So if my population size is 100, I've got 15, I'm going to generate 85 children, right, and put them into the next population. So I'm going to say let parent 1 equal roulette wheel select from the population with the sum. That is my first parent. Okay? So what is roulette wheel select? I go down here. Here is where you implement roulette wheel selection. So over here, you're going to copy and paste this. You're going to put it over here, and you're going to turn it into JavaScript. Okay? Pretty simple. That's the algorithm that we talked about. It will return one parent. Then we need a second parent, and we call roulette wheel selection again. Now, as you can see here, there are no checks to see if both parents are the same. That's okay. I don't really care. I don't think it makes a big difference in this assignment. But in a real GA, you may have some sort of mechanism in there to say, you know, maybe select two parents, don't have them both be the same. Next, we've got both the parents. So the next step to the GA, if I go down here again, is to combine the parents to form offspring. So child 1 is the crossover of, and what we're going to be doing for this assignment is the first half of the first variable and the second half of the second variable. And we get passed in the settings as well because we need the mutation rate. So let's look at how that works. Here is crossover. So we're going to generate child gene, okay? Add the first half of parent 1 to child gene, add the second half of parent 2 to child gene. Now, be very careful because the size of the child gene must equal the size of the parent gene, and when the size of the parent is odd, there's no exact half, right? So choose 1 to the left or 1 to the right of the midpoint. So if I have a gene length of 5, for example, maybe I add the first 2 and the last 3, right? If it's even, it's super easy. You just take the first half and the second half. Just be aware that for odd ones, it's, your program crashes. Why? It's probably for that. And then this is actually done for you. Return this. So you may be asking yourself, why am I... oh, no, never mind. So what we do is create the child gene, and then we create a new individual, which is an object consisting of a gene, and then the fitness of that gene being calculated. Okay, so when we generate the child, that's when we have the fitness. So we do that again, but we pass in the parents in reverse. So we get the first half of the second half of the first. And then we're going to mutate those individuals, right? So the mutate individual down here, we get passed in an individual, and we get passed in settings. And we say mutate changes a random index of the gene to a random gene value. So we're going to take that individual, and if we should mutate it, then we are going to change one of its values to a random value. So how do I know if I should mutate it? Well, as I said before, settings.mutationRate, that is the number of things, approximately, that should be mutated. So I'm going to generate a random number between 0 and 1, and if that is less than the mutation rate, then I generate it, right? So it might be pretty obvious to some, but the way this works, generate a random number between 0 and 1. If I have a mutation rate of 0.1, that means I want to mutate 10% of things. What's the chance that a random number between 0 and 1 is less than 0.1? It's about 10%, right? So that's the way we do that. And this function modifies the individual and returns nothing. So we look at individual.gene, find a random index, change it to a random value, and then that's it. It's already modified. However, something that I gave this course for 5 years before I found this bug last year. If we mutate something, we've changed its fitness value. So last year, I noticed that I had a solved board on a 2x2. The fitness value was the fitness value of something that was solved. But on the visualization, it wasn't solved. Like the numbers were wrong. And it was because I had taken a solved board and mutated it and then didn't re-evaluate it. And so what you have to do there, and I've already done this for you, is just after you mutate something, recalculate the fitness. That was the bug that I found last year, and now it all works correctly. And what happens next? Add the children to the population. One tricky thing here is for each set of parents, we're going to generate 2 children by default. But in this example, I started with 15. I need to get to 100. That's an odd number of things. So you have to be sure not to add the second child if it would make the population go over, right? Because if I just added both of these children and had this while loop up here, then my population would actually be 101 instead of 100. Because I stopped, I went, okay, 15, 17, 19, 21, all the way up to 99, and then I added 2. So I got to be sure, after I add the first one, don't add the second one if it will go over the population size. So the next population array should always have the same settings.population size. So while you're debugging, while you're making sure everything works, you can put a little check in there if you want to make sure that you're doing it correctly. And then you have to return next population. Okay, I've got population here just so the UI didn't break, but this should return that next population that you did up here. Okay, There's one other thing that you have to do, but I'll get to that when I look at the marks. So this is the grading. And yeah, let's look over this because it'll explain some stuff. So we've got the standard 5% for not being sloppy. Then I've got 30% for the GA functionality. So the way that I'm going to grade your assignment is that it should pretty easily solve a 2x2 Sudoku. Like, not instantaneously, but we'll put the TA will put a 2x2 Sudoku, and within a few seconds, 10, 20, 30 seconds, you should have a solved 2x2, right? So that's one of the goals that you have to meet. You should make significant progress toward a 3x3 Sudoku. There should be a few things left on the board, maybe like less than 10 after a little bit of calculation. You have to be able to solve all of the non-Sudoku fitnesses for 9x9, actually for anything. So if I go to here, you should solve this eventually. It's a convex problem, and this is how I actually recommend debugging your program. So you will know when your GA is working if some values is being solved easily, right? If you put it on some values and this isn't going up, then something's wrong with your GA. These are the ones that I recommend debugging your algorithm. And then once you know your algorithm is working because it's solving these convex problems, then go back and start the progress on the Sudoku stuff. The individual functions that we're going to mark, I don't need to repeat them all. So the child generation has to be correct, random individuals, elite survival, et cetera, et cetera. And then for 6980, this is the grad version that you have to do, is I want you to use your brains, okay? So in addition to going out and making a new Sudoku fitness function, I want you to go out into the wild and explore what people do to make GAs better. Take one of those things that you think is feasible and implement it. So there are thousands of improvements that people have made to genetic algorithms. And I just want you to implement one of them, okay? So for example, and maybe everyone does this because it's the thing that I mentioned, but what some people do, if they get, oh look, my results are pretty stagnant, but I know I'm not solved, maybe I could dynamically modify some of my settings. Actually, don't do that one because that's the easiest possible thing, and I don't want that to happen. But for example, maybe you could do some Sudoku-specific mutations, right? So maybe I'm taking rows from each board and putting those together. Maybe that's a better way to do it than just splitting it down the middle, right? If you do something that is, for example, I'm going to have an entirely new way to do the mutation, then what I want you to do is create a new function which is like better mutation, and then you call that instead of having a bunch of code because I want to know that you did the assignment correctly so that I can just set mutate individual, and also you have the new mutate function. Or, hey, maybe there's something that's way better than roulette wheel selection. So you could also implement that thing, okay? And ideally what I would want you to do is when you have that finished, and actually let me just put this up here. So let use improvement equal false. And so if that is false, I want it to do the base functionality of the assignment. If it's true, I want it to use your new modification. And so this is if true uses your new modification, please explain in a comment what your modification is. Okay? So that's 10%. Grad students have to go out, do a little bit of research. Wherever you get your idea from, just cite it. Okay? I want to know where you got that idea from. If it was from a paper or a website, ideally not Wikipedia. This is just to get you to explore, because this assignment is like 40 lines of code. It's not that hard, right? The only real hard thing is you thinking about the new Sudoku function and this part. So go out, explore, find something. This does not need to be genius, okay? I just want you to do something that was above and beyond the default assignment. And I believe that's it. Oh no, let me go down. and just make sure I got everything in the marks. Yeah, so that's 10% of the assignment, total mark 100, and you are only submitting this GA student file. Any questions about any of the assignment stuff? Okay, you're all familiar with how this works by now. Have fun. I think this is a pretty fun assignment, and you'll know if it's working because the line goes up, right? And if I go over here, excuse me, what you will get, you will not be getting the solution code. So I'm not giving you obfuscated solution code for this one, just like I didn't for the last one, because it's just like, you know what it will do, right? You don't need to look at that. So by default, when you get it, it will look like this. And it literally just returns, it creates the randomized population, and then it does nothing. It returns the previous population. So it's all just there. And one other little thing that I want to show as a little hint is if you look at GA GUI, in here, where is it? Yeah, set up the initial population. This is the code that goes through settings.population size, creates random genes, and then creates individuals based on those random genes and adds them to the population. So if for whatever reason you can't remember the syntax or you don't know how to create random genes, it's right there for you, right? So if you just, whenever you're adding random genes, if all you do is change this, then that's the random gene code done for you, right? Because this is inserting random genes into the whole population. All you need to do is change that. So I just wanted to let you know that you are free to use that code, because some people are afraid to like copy and paste my code sometimes. But if I've already done it, then feel free to.